Okay, so let me get started. Welcome everybody to our first Zoom distinguished seminar series. We are taking advantage, I suppose, of this unusual situation, and this way of delivering the interesting stories will stay with us for sure. That doesn't mean that we will not actually have real people showing up at the real seminars, but this is going to be a good supplement. And we do have, of course, distinguished speakers right here and at Waterloo, and it's my pleasure to welcome today Chris Wilson. By the way, I'm Zbigniew Wasilewski, and I'm hosting this first talk. Chris has been with us at the University of Waterloo since 2012. At this point, in the capacity of full professor and director of the graduate studies at IQC. So he's EC and IQC faculty. His path sort of into research started or science at MIT, and he graduated in 1996 from doing things which were not necessarily quantum, but kind of close, doing some simulations of nonlinear dynamics of nervous system. And then he did his PhD at Yale University in 2002. That was already seriously quantum, and then moved on to Chalmers University of Technology in Sweden, where he stayed till effectively 2012. But in 2011 he took sabbatical again, kind of into biomedical startup. So clearly his interests are much broader than quantum, and from Chalmers, where he was a faculty, he actually joined University of Waterloo in 2012, and from there on, basically carrying on in his quantum quest. Okay, so today Chris will be talking about some microwave quantum photons. I don't have the title of your seminar in front of me, but I hope that I'm not too far away from that. Okay, so Chris, the floor is yours, so to speak. Okay, thank you. I'll just mute and disappear. But one other comment here. In principle, you have the two options to ask questions, which is the chat and the question and answers. But use the questions answers. Apparently, it's more friendly. And then if somebody asks questions which you also would like to ask, you can put the thumbs up there or something to reinforce it. So definitely we'll get more attention, okay? All right, so I am off from the video and handing it over to Chris.
Okay, so here, let me just start sharing my screen and get the presentation going. So people see my slide again? Okay. Okay, so anyway, so my name is, as Big said, Christopher Wilson. So I'm a professor here at UW in the ECE department and also at IQC. And so say I run experiments using superconducting quantum circuits. So we do some things related to quantum computing. We also have a lot of stuff looking at what we might call microwave quantum optics, or trying to use quantum circuits to make quantum states of microwave light, or non-classical. So just a second. Okay, there we go. let me start, and let me say in general here, since I know it's a kind of a diverse audience, I've made a real effort to have a longer introduction where I explain some concepts about what I mean by non-classical or quantum states of light. And then in the second half of the talk, I'll go over some experiments that we've done trying to make these non-classical states. So let's just begin at the beginning. What do I mean by a non-classical or quantum state of light? So in words, a non-classical state of the electromagnetic field can produce measurement outcomes that cannot be predicted or reproduced by Maxwell's equations. So classical physics, electromagnetic field is governed by Maxwell's equations, but sometimes in the quantum world, we can get outcomes or measurements that are different. Now, typically, these things only appear, these non-classical effects will often only appear in statistics at higher order, so we have to look at variance or correlations or higher order statistics. We typically don't see them in averages, so they're somewhat hard to find. And just to make clear, this doesn't mean that Maxwell's equations go out the window when we start talking about quantum. 99% is still Maxwell's equations, and there's just some fine details that come from the quantum aspect of light. So just to clarify a bit more, we can also, let me say what we think of, at least in the language of quantum optics, as classical states of light, or what do I mean by that? So the two most common ones are first what we call a coherent state, which is basically the output of a laser in the optical regime, or the output of a microwave generator in the microwave regime. So this is really what we think of essentially as a classical signal. And then the other classical state is a thermal state, which is basically, again, in the optical, the output of a lamp, or in microwave or lower, it's the output of a resistor. So other words for this would be black body radiation, or in the electrical regime, this is just Johnson noise of a resistor, for instance. So then what would be some non-classical states or quantum states of light? So there are a variety of them, and three common ones, all of which I'll touch on today, are single photons, so true single photons. We can have entangled states, so we have states of light which show entanglement, which I'll also talk about. And then a third one is the quantum vacuum. So as I'll describe later, emptiness is not empty in quantum mechanics, and that can have some interesting consequences. So going a bit further, let me start by talking about single photons. Let me introduce some of the concepts. So we're all familiar with the idea with the wave nature of light as described by Maxwell's equations. And I'm sure we've also all heard of the fact that light is made up of discrete quanta or particles that we call photons. And it's one of these kind of standard paradoxes of quantum mechanics that light can be both a particle and wave. But what does that really mean? Or how could we tell the difference between a particle and a wave? So there are various ways to do this, but one is to look at the statistics of the light when it's divided on a beam splitter. So this is a famous experiment called Hanbury-Brown twist, but so in the optical frequencies, a beam splitter is a partially silvered mirror. So a beam can come in, it hits this thing, some of it's transmitted, some of it's reflected. But also in the microwave regime, we could think of this as being a power splitter or a hybrid coupler. And so for a classical wave, I didn't make my line wavy here, but that's the idea. I have a classical wave or signal coming into this beam splitter, and it can just be split into, half goes one way, half goes the other way. And I just get two perfect copies, or I get two copies of the beam that are very well correlated. And so again, in kind of microwaves or RF, just think about the splitter you use to bring your cable to two different TVs, right? I can split the TV signal and watch it on both TVs. There's no issue. But if we thought of light as being made of particles, we get a different situation, right? So now we imagine having a discrete stream of particles coming to our beam splitter. So our discrete photons that are well separated, discrete single photons. Now, when these photons hit the beam splitter, something different happened. So essentially, they have to choose which way they want to go, right? So if one goes to output 2, it means one doesn't go to output 1. And if one goes to output 1, it means it doesn't go to output 2. And so this means that when we have photons or well-defined photons, we expect, instead of to see correlated signals at the output of the beam splitter, we expect to see anti-correlated signals at the output of the beam splitter. So this is the big this is one way to tell the difference between waves and particle-like behavior. So we get this basic, here I'm introducing this basic idea that I had mentioned, that by looking at statistics of our signals, sometimes we can distinguish between kind of classical behavior and quantum behavior. And here's just a quick example to show some data. I mean, this is an old experiment that we did in 2012 when I was at Chalmers. And we're doing exactly what I said. I have a microwave beam splitter, which is just a microwave hybrid or directional coupler. And here I start with putting in some kind of classical state, so say a thermal state. So again, just the output of it's just the Johnson noise of a resistor. And then I look at the correlations between these two beams, or the two outputs of the hybrid, the two outputs of the beam splitter. I'm plotting the somewhat funny function from quantum optics, which is called G2. But this is basically just 1 plus the power correlations. And what I can see, in this plot, this correlation function. So this is just, the power correlation as a function of a time lag between the two states. At 0 time lag, this thermal state has kind of perfect correlation. G2 of 2 means correlation coefficient of 1. So there's perfect correlation between the two outputs of the beam splitter, like we expect for a classical state. But if I do the same thing for my single photon, so I'll talk a bit more later on about how I might make a single photon source in the microwaves. But for now, just believe me that I can. But anyway, so we take this stream of single microwave photons, put it at the same beam splitter, and then measure again this G2 function, or just the power correlations. And like we expect, what we see is now negative correlations or anti-correlation, which makes the G2 drop below 1. So we kind of see very clearly here that we get the statistics here reveal the nature, kind of particle versus wave nature of the light. And just as a comment, as we go on, I'll talk more about experimental details, but these are fabulously hard experiments to do because microwave photons are tiny. The amount of energy in a single microwave photon is very small. And we have noise and we have background noise. So for instance, here to get 1 point of data, we had to average about 3 terabytes of raw data over kind of processed in real time over 17 hours. So yeah, these are hard experiments. So that's kind of a brief introduction to single photons. Now we can think about, let me now talk about vacuum fluctuations, or the quantum vacuum. So what are quantum vacuum fluctuations again? So probably most of you have heard of the Heisenberg uncertainty principle, which comes out of quantum mechanics. And so this tells us for, say, a particle, the position and momentum can never be perfectly known at the same time. And this is commonly expressed as this inequality. So have the product of the position times the product of the momentum is greater than or equal to h bar over 2. Now this has essentially, so this uncertainty principle essentially has a corollary, which we could say is that a quantum particle can never be at rest. And that's because if it were at rest, you would know where it was, you would know its position, and you would know it's not moving. So you would know its momentum with infinite precision. So quantum particles are always a little bit fussy. They always have to move around. This is called 0-point fluctuations often. And now when we get into the language of quantum field theory that we use to describe the electromagnetic field, we get essentially a generalization of this. So it's the same thing, vacuum fluctuations, or when we say vacuum fluctuations, excuse me, these are the 0-point fluctuations of the electromagnetic field. So it simply says that the electromagnetic field can never be perfectly quiet. There's always some amount of noise or vacuum noise in the electromagnetic field. And so these vacuum fluctuations have a kind of long and somewhat elusive history in quantum theory in terms of how they might be observed. So I think one of the first suggestions of an impact of vacuum fluctuation came in the 20s or 30s as an answer to kind of a paradox about the stability of excited atomic states. So we'd say in quantum mechanics, since all atomic orbitals, so we can think of like S and P and things like that. So since all atomic orbitals are stationary solutions of the Schrodinger equation, or in more quantum-y language, they're eigenstates of the Hamiltonian, even excited states of atoms should be stable. So, you know, I should be able to excite an atom and it shouldn't decay if that's all that's going on. But they're not. We know they're not. And so Dirac suggested that it could, in fact, be vacuum fluctuations that were responsible for this. So I put the atom into the excited state, and vacuum fluctuations disturb them, and this causes the phenomenon that we call spontaneous emission. So when the excited state decays, and in the process emits a photon. So that was a qualitative suggestion, but the first quantitative suggestion, or the first quantitative experiment and prediction related to vacuum fluctuations was the Lamb shift, measured by Lamb and Rutherford in 1947. And so quickly what the Lamb shift is the Dirac equation, which is just a relativistic version of the Schrodinger equation, predicts that the 2s and 2p energy levels of a hydrogen atom or orbitals should have the same energy. But experimentally, Lamb and Rutherford saw that they don't have the same energy. So there was a shift in the energy of one of the levels. And later on, it was shown through rigorous calculations that it was in fact vacuum fluctuations that caused this shift or this split. So essentially the 2s and 2p orbitals have different shapes, so the vacuum fluctuations affect them differently. And that leads to this tiny shift. And just a quick note, because it also will be relevant later, in modern times, so it's actually in the field of quantum computing, which I also work in, spontaneous emission of quantum bits. So when I'm trying to process things on my quantum computer, I'm exciting quantum bits, but they have a tendency to want to just give up to spontaneously emit and relax energy to the environment. And this is caused by vacuum fluctuations. And this is actually a major design constraint for quantum computers. So in 2020, vacuum fluctuations have a real technological impact on quantum technologies. And there's something that kind of quantum engineers have to work around. So just described in terms of this relaxation, and it's a constraint on quantum computers, the quantum vacuum can have negative effects. But it also turns out it can be a valuable quantum resource if we treat it the right way. So to kind of see how this can happen, we have to take a somewhat different view of vacuum fluctuations. So I already mentioned the idea that I can just think of them arising from the uncertainty principle, but in a more full quantum field theory treatment, we can also think of them as arising from pairs of virtual particles and antiparticles that constantly pop in and out of existence from the vacuum. So this would happen with all quantum fields. So for electrons and positrons are constantly popping in and out of the vacuum and annihilating. And just the same goes for photons, except photons are their own antiparticles. But then it's just these photons popping in and out of existence is what is we see as causing the vacuum fluctuation, somewhat strangely, these virtual particles. So if we see virtual fluctuations as arising from photon bubbles, one could whimsically ask, is it possible for these bubbles to be popped or broken? And in the 1970s, surprisingly enough, a number of physicists predicted that the answer was yes. So there was a series of papers predicting different effects, related effects, with names like Hawking radiation and the dynamical Casimir effect and the Unruh effect. that predicted that there were ways to essentially break these photon bubbles and extract real photons or convert these virtual photons into real photons that could be measured. Now, the downside of some of these original proposals is that you needed things like black holes for Hawking radiation or mirrors moving at near the speed of light to extract these photons. And let me give a sense of how this could happen. So for one of these effects called the dynamical Casimir effects, I mean, it's a very cartoony idea. The idea is imagine that you had one of these bubbles starting to form, or this bubble is formed, and then I have two photons pop into existence. And now before these photons can find each other again, or before the photon can find its partner and disappear, imagine I can kind of very quickly, so near the speed of light, move a mirror in and kind of swap the photons away. So they reflect off the mirror and they head out to infinity and they don't find each other again, and they're converted into real photons with the energy coming from the mirror itself. So this was predicted, and there's actually a bonus which is relevant now, which is that not only are we getting photons from the vacuum, which is some interesting way to explore them, but it's predicted that these photons should also be entangled. So there's a certain takeaway that, well, if we can play the right tricks, the quantum vacuum can be a source of entanglement, which is an important resource for quantum technologies that I'll talk about. And just to mention, by the way, now more than 10 years ago, we were actually able to demonstrate the dynamical Casimir effect in a superconducting circuit. So although it sounds quite exotic, it is something that's been done in the lab now. So here I am talking about the quantum vacuum, but one could ask, I mean, how do we make the quantum vacuum, or how do we access the quantum vacuum in the lab? And as it turns out, there's a natural way to do that, which is through cryogenics. And so what do I mean? So we can just look at, as I can say, ask Planck. So here is a formula that tells us if I have some mode of the electromagnetic field, so I have a black box, or I have some cavity or a microwave cavity, this tells me what's the average number of photons in that mode as a function of the frequency and temperature of the mode. So this is the Planck formula, and in the limit of low temperature or high frequency, it just becomes this decaying exponential. And so what this tells me is that at low temperatures, thermal or black body photons are exponentially suppressed. So one way to prepare electromagnetic vacuum is simply to cool things to low temperature. And just to give some numbers, at 50 millikelvin, which certainly sounds like a somewhat exotic temperature, and at 5 gigahertz, which is a typical microwave frequency, this number of average thermal photons is less than 0.01. So if I can cool to kind of 50 millikelvin or below, I can access really a quantum vacuum. So there's just no thermal photons around. The electromagnetic field is in its vacuum state. So one might ask, of course, how do I access the quantum vacuum? And how do I access these temperatures? And as it turns out, they're relatively accessible these days, or at least I can just buy equipment that gets me there. So this is a photo from my lab. And this big thing here is what we call a dilution refrigerator. And I'm not going to talk in any great detail, but the point is it's a cryostat. So this is a thing that can cool several kilograms of copper, including our devices, down to, in fact, say 10 millikelvin. And it's a complex machine. Behind this wall are tons of pumps and things like that do it. And then over here is our microwave equipment. We can also look inside of this dilution refrigerator. So this is with the vacuum cans off. And what you see, again, I'm not going to take too much time, there's a bunch of different plates here. Each of these plates gets to a different temperature through a different cooling process. So 3 Kelvin, 800 millikelvin, 100 millikelvin, and then 10 millikelvin. And you can also see here we have kind of microwave coaxes, and we have microwave circulators and various things, microwave amplifiers. And then our sample sits at the bottom. So we might have our sample in a little microwave tight or light tight box, again with microwave cables connected to it so we can so we can talk to the device. So vacuum is another interesting state. It's a problem for us sometimes. We have to engineer around its noise, but it's also a resource. It can give us entangled photons. And so let me now talk a bit more about entangled photons, or what entanglement is. So entanglement is one of those, I'm sure you've all heard of entanglement, or many of you have. And this is often described or talked about as this kind of weird or mysterious quantum thing. And not to say that it isn't weird and mysterious, but at the same time, it has some important features that are more accessible. And in particular, we say that two systems are entangled, or when we say that two systems are entangled, what we mean is that there are correlations between the two systems that are stronger than is what allowed by classical physics. And I'll make that a bit more clear, but that's the point. Entanglement means we have extra correlations that can potentially be exploited for quantum technologies. And entanglement, in fact, is a key resource for quantum communication and quantum sensing. There's still debate, but entanglement in particular may be a key resource for quantum computing or other types of quantum correlation. So let me try to give a little bit more of a feel of what I mean by these correlations and strong correlations and things like that. And so I'll talk a bit about a particular type of entanglement. So there are different types of entanglement, but I'll talk about one type, which for the expert is called continuous variable entanglement, which is relevant to us because we work with continuous variables like voltage. But in any case, let's start by imagining that I measure two signals. So here is, I have a blue signal and my red signal, which look like noise here, which are noise. And this is actually real data. So this is just measured quadrature voltages from a microwave field. So I can ask how similar these two signals are, even though they're noisy. And we usually do that by measuring correlation or covariance. So the correlation tells us how similar they are. Or more precisely, statistically, we can characterize these two signals with a few numbers. So the power in each signal, and also the correlation or covariance between them. So as it turns out, I can write then, with these numbers, the power and the covariance, I can write down a very simple bound on how classically correlated two signals can be, or what it means for them to be entangled. And it's for the simplest case where the two powers are equal, so I just have 1p, the bound is just this here. So it just says that if the covariance between the signals is greater than the power in the signals minus 1, and in these units, 1 here is the 1 unit of vacuum noise. So if the covariance is greater than the power minus the vacuum noise, then the signals are entangled. Or it says, we can turn this around and say that this is a bound on classical correlation. So correlations of classical signals have to be less than this p minus 1. So this bound is derived very rigorously from something called the positive partial transpose test of the density matrices. But we can also give a kind of hand-wavy explanation of what this means and where it comes from. So to do that, we imagine that we're going to try to make two perfect classical copies of a signal. So we have a signal S that we want two copies of. So this is just a classical signal, and we're making a copy A and B, but in a quantum world, which we believe we are, if I have this, I can have this perfect classical copy, but I have to at least also have vacuum noise if I just make these two copies. So I have my signal S plus vacuum mode, the vacuum noise of signal A, mode A, and the vacuum noise of mode B. Now, if I simply just now try to calculate the power and covariance or cross power of these signals, I see that, say, if I just square A, I get the power in S, but also the vacuum noise power. So I get S plus 1. The vacuum noise contributes to the power in the signal. But when I measure the cross correlations, so I get S squared because S appears in both of them, But as long as these two modes are independent, the vacuum noise is also uncorrelated or independent. So it doesn't contribute to the covariance. So putting these together, what I see is that putting these all together, I see that the correlation in my signal is exactly, C equals P minus 1. So this kind of, this kind of hand-wavy derivation gives me exactly the bound on the classical correlations. And I think this really gives a physical meaning of what this means. Okay, so that was my kind of quick introduction to non-classical states. And let me now, or not that quick, it's half my talk, which was the plan. But in any case, let me now talk about some experiments that we've done in our lab where we try to produce some of these non-classical states, so produce them and measure them. This first experiment, I'll talk about a source of single microwaves that we developed. In addition to just producing single microwave photons, we can say it was an on-demand source, and it could change and control the shape of the microwaves. And I'll explain what all of that means. But as a brief introduction to that, a brief motivation for this section, I'll start with some kind of faraway or potential application as motivation. So I'll start with a cartoon taken from a 2008 Nature paper entitled "The Quantum Internet," which shows the basic idea of some kind of a quantum internet or quantum network. So very much like a classical network, it is made of nodes, so quantum nodes, and then channels that carry information between the nodes. And now these quantum nodes may have some ability to do basic quantum information processing, or routing and things like that. And again, the channels just will carry information, but they can also carry quantum information, not just classical information between the nodes. And taken together, these nodes and channels make a basic quantum computing or communication network. Very much an analogy to the classical one. And we can also say that this can also be a model for a kind of scalable quantum computer in much the same way that modern supercomputers often have many small processing nodes that are all connected together. Now, there are many candidate ways to build these nodes. So people use atoms, people use superconducting qubits, people use other solid state systems, all possible kinds of things. But pretty much it's understood that for the quantum channels, or to transmit information between the nodes, we want to use photons. There could be optical photons or microwave photons, but we know that photons travel well. And we use microwaves for our cell phones, and we use optical photons in fibers and everything like that. So they're good information carriers over distances. And with that in mind, though, we could think of a wish list for a photon source that we could use to connect quantum nodes. And there's some ideas of high fidelity, high efficiency, which just means kind of generally it works well. But we could also say that we want an on-demand source. So many existing sources or different things are stochastic or random. So they can generate single photons, but they do so randomly or at random times, which is not, which decreases their usefulness. We could also say we want to be able to encode quantum information or encode qubit information in the states. Another thing which may be a little bit less obvious is that we also want to be able to shape the qubit wave packets, as we kind of see here. And this has to do with the fact that often these quantum nodes might be some kind of resonant cavity, and to get photons in and out of the resonant cavity without having a lot of loss, you have to match, you need a particular shape to the photons, or you need to match the mode shape of the quantum receiver if you want to get good, if you want to have high efficiency absorption of the photons that are sent. So shaping the single photon wave packets is important in this quantum regime. So we want to make single photons. So how do we do that? So there are various ways to do that, but one of the kind of oldest ones and classic ones is to generate single photons is to use single atoms, right? So we can have a sense that single atoms are already some kind of quantum thing. So, and then, what I can do is I can imagine hitting this single atom with a laser, which is, as we said, is a classical source from our point of view. So, and it also has many, many photons. But this atom will absorb can absorb just one of these photons. And then if we wait some time later, it will spontaneously decay, or through spontaneous emission, it will emit that single photon. And so I can get I start from a classical light field, and I get out just a single photon, which you said is a non-classical light field. So people do this in the optical regime, but what can we do in the microwave regime? And so we're going to generate that, or sorry, we're going to generalize that. So we're going to make our single photons, instead of from single atoms, we're going to make them from single artificial atoms. And it's the same idea. We're going to have a single artificial atom, which I'll describe what that is, or qubits. So we're going to hit that with a bright microwave field from our microwave generator, and then we're going to wait, and then that thing is going to decay and emit a single photon again. So sounds simple, but of course, what do I mean by an artificial atom made from a microwave circuit? Or what do I mean by a superconducting qubit? So if I want to start thinking about making some kind of quantized electrical circuit, I can start thinking about the simplest circuit in the microwave or electronics, which is just a harmonic oscillator, or an LC circuit here. Now I can go through an exercise of quantizing this thing, but it turns out it doesn't make a good qubit or artificial atom, and that's exactly because it's harmonic. So over here, I've drawn a kind of energy level diagram of the circuit, and I see that, so I have energy of 0 photons, 1 photon, 2, 3, and these are all equally spaced because it's harmonic. So its frequency doesn't depend on power or the number of photons in it. And this is bad for quantum control, because if I try to excite, say, the 0-1 transition, I'll also excite 1 to 2 and 2 to 3. So I can't control the state of the system. So what can I do to improve the situation? Well, one thing I can do is essentially just replace that linear inductor by a very nonlinear inductor. And if I can really make that nonlinearity large enough, essentially what I get is now an anharmonic oscillator where the energy levels aren't equally spaced. So with a sufficiently nonlinear inductor, I now have, say, a 0-1 transition, which is different from the 1-2 transition. And I can address just the 0-1 transition, and I can do kind of quantum control, or I can put just one photon into my oscillator, which I can then expect to get out. So I don't want to spend too much time on the superconducting physics, but let me quickly say what this nonlinear inductor is. And it's a very standard tool of the superconducting community, which is called a Josephson junction. So a Josephson junction is just a name for a tunnel junction between two superconductors. And in our case, the two superconductors are just aluminum, so very, very standard metal. And then the tunnel barrier just means that I have a very thin insulating barrier between my two electrodes. So that's what I've kind of indicated here. I have two superconductors S with a barrier in between them. And classically, no electrons can flow through the insulator, but quantum mechanically, if it's very thin, the kind of wave function of the electrons can leak through, and I can get transport across. Now, I'm not going to go into a lot of detail about Josephson junctions, but I can write down the current voltage characteristic of the Josephson junction, which is described by these two equations, which are called the Josephson equations. And what I can see is that it's a, well, I'll put those there. And to interpret these, let me also just write down the constitutive relationship of just a standard linear inductor, right? So this is just the current voltage characteristic of a standard inductor written in integral form. So the current in the inductor is just proportional to the time integral of the voltage. And I see now, looking back at the Josephson junction, I can see, well, I have this one variable I call phi, which is just this time integral of the voltage with some constants. And then I see that the current is now a nonlinear function of the time integral of the voltage. It's a sine, but you can see that if I expand the sine to first order, so if I have small oscillations, I just get, again, back that the current is proportional to the time integral of the voltage. So I can see here then that for small oscillations, the Josephson junction is just an inductor. And if I have bigger oscillations, well, it just becomes nonlinear. So I get a nonlinear inductance from the Josephson junction. I'll just show real quick, what does this really look like? So here's a nanoscale Josephson junction made in the quantum nanofab in the QNC building. And what I can see here is I have an aluminum, so the size bar here is 300 nanometers. So you can see I have an aluminum electrode, and it's small enough that I can see individual grains of aluminum in the film. And then I have an aluminum counter electrode. And this overlap area defines my junction, and not visible because it's so thin is a layer of aluminum oxide, which is just native oxide grown on the films, which is only 1 or 2 atomic layers thick, so very, very thin. And while we're talking about junctions and devices, let me quickly introduce one other Josephson junction device, which is something called a SQUID, which stands for Superconducting Quantum Interference Device, which is nothing more than 2 Josephson junctions in parallel forming a loop. And what the SQUID does is it, for the point of view of this talk, is it actually just gives us a tunable inductance. So if I put a magnetic field through this loop or a magnetic flux, it changes the inductance between these 2 terminals. So the SQUID, the Josephson junction gives me this highly nonlinear inductance, and a SQUID gives me a tunable inductance. So now I've described what our artificial atom is. It's just a highly nonlinear inductance, it's just a highly nonlinear oscillator or anharmonic oscillator. And so back to this picture, what I see, whoops, in the center here is exactly just my qubit. So this is the qubit here, and what these the 2 paddles that you see here are really just the paddles of a planar capacitor. So this is the C in my LC. And the Josephson junction is just in the middle here, and you can't see it because it's tiny. These capacitor plates are hundreds of microns, and the Josephson junctions are hundreds of nanometers. And then the rest of this here, this is just a coplanar waveguide. So this is just a planar microwave transmission line. So this allows us to bring our signals in and out and talk to our qubit. So as my animation, here I'll go back and redo my animation. So again, we're going to try to make now our single photon out of our single atom by essentially just hitting our artificial atom with a big microwave field from our generator. And then we're going to wait for it to decay and emit our single photon, because it can only absorb a single photon there. But what I said is we want to be able to control this a bit better. I mean, we can do that. It emits single photons, but the emission time is completely random, which isn't great. So how can we think of controlling the emission of the qubit? Well, first of all, we could think of what sets the emission rate. And so at t equals 0 or near 0 temperature, which again, we reach with our dilution refrigerator, this emission rate or relaxation rate can be written like this. So it's basically, so gamma 1 is the emission rate, and it's proportional to the vacuum spectral density of, or the spectral density of vacuum fluctuations. So it's how strong are the vacuum fluctuations that the qubit sees, and then times a coupling constant. So just how strongly coupled, which in this case is really just the capacitive coupling between the qubit and my transmission line. So if we wanted to tune the emission strength or emission rate, we can see obviously we can do it in 2 ways. So either we can change this coupling constant, which would mean changing the coupling capacitance in situ, or we can tune the strength of vacuum fluctuation. And that sounds a little weird, but I like playing with vacuum fluctuations. So we could think about how can we do this? So how can we tune the strength of quantum vacuum fluctuations? Very conveniently, even though we're thinking about vacuum fluctuations, we can still use our classical intuition Because as I said, the spatial and temporal modes of the vacuum are still governed by Maxwell's equations. So Maxwell's equations still tell us the shape of the vacuum, or they tell us how it responds to things, or some of how it responds, just as it does for classical fields. So if we could think, with that in mind, this cartoon gives us this idea of how we can think about affecting vacuum fluctuations. So imagine we put our qubit, which is this thing here, this little strange object here, into a semi-infinite transmission line. So I have this transmission line on chip. On this side, it's just going off to infinity, to my amplifier, or whatever I want. But on this side, I terminate the field, I terminate the transmission line on one side. So I connect it to ground, let's say, through a short. And so if I terminate this transmission line, at a given frequency, what I do is I create a standing wave pattern. So if I put in a classical signal, I would get this standing wave pattern determined by the boundary condition here. But as it turns out, the same thing happens to the quantum vacuum. So this boundary condition changes the shape of the quantum vacuum, and I get a standing wave in the strength of the vacuum fluctuation. And then what I can imagine doing to change that is I just say, instead of shorting my transmission line, I put a squid here, which is again just this tunable inductance. So instead of having a dead short to ground, I have some inductance, which gives me some impedance at the given frequency. And if I can change that inductance, I can change this impedance, and I change this boundary condition. And the effect kind of down the line that my qubit sees is the vacuum fluctuations, or the modes of the vacuum fluctuations are moving back and forth. And so you could imagine if I design things properly, I could have that, for, very small inductance or a short, the qubit is sitting at a node of the vacuum fluctuation. So it sees essentially zero strength of the vacuum fluctuations. But if I, push the vacuum fluctuations a little bit, now the qubit sits with this blue at a point where there's finite vacuum fluctuation. So I can change the boundary condition, kind of like moving a mirror back and forth, and I can push the shape of the vacuum fluctuations back and forth. And that way effectively change the strength of vacuum fluctuations, change the relaxation rate of the qubit. So this is what this device looks like in real life. So again, this is a microwave circuit made in the quantum nanofab here at IQC. I'm using a combination of optical and e-beam lithography. So I have here just I have my coplanar waveguide coming in that's meandered to make it more compact so I can talk to things. I have the end of my transmission line where the transmission line is terminated in a squid. So I see this loop of the squid. This is a line that allows me to bring in fast currents, microwave currents to do fast tuning of the squid. Here is my qubit, which is sitting like a wavelength away from the end of the transmission line. And again, here you see the interdigitated planar capacitor of the qubit and the junction in the middle. And then, as a detail, but it'll be important on the side, I have a second kind of side microwave gate that has a very weak coupling to the qubit, but it allows me to still kind of excite the qubit kind of independent of how strongly it's coupled to this transmission line. Okay. So we can think about measuring this device. And so this is how I probe this thing is just by putting in with a vector network analyzer. So I just measure, I put in a microwave field and I look at what's reflected. Far away from the qubit frequency, I get no reflection, or I get perfect reflection. The reflection coefficient is 1, and near the qubit, I get a dip in the reflection. And this tells me the qubit frequency. And if I do this for a bunch of magnetic fields, I get something like this. So here now is my qubit probe frequency, and here is the flux. And what you see is that there's a little bit of frequency variation, which is essentially parasitic, but I see the width of this transition is changing dramatically. And that's telling me that the qubit is kind of strongly coupled here and weakly coupled there, and even completely decoupled almost there. I can fit that and extract kind of exact rates. So gamma 1 I want to focus on here. So I can go from kind of 2 megahertz emission rate to kind of a unmeasurable coupling rate down here. To get my single photon, so the idea, like I was saying here, is that I could, what I do is I use my side gate to excite the qubit with an intense field. And then I look at the emission in the line. And so this is actually, so we have to average, we expect single photons to be coming out. So I need to average a lot. But when I do that, I see this microwave voltage, which has this exponential decay, which is just the decay time or the coupling rate of my qubit. I really see here a single photon coming out of the qubit. And now the interesting thing, well, here, I'll skip this. The interesting thing, like I said, the way we make this thing on demand is because now we can control this coupling rate. You know, what we can do is we use a pulse, it's a fast pulse, to put the qubit at a flux point where it's decoupled from the transmission line. And then we excite it through the side gate. So here you see is a little bit of leakage of our excitation pulse from the side gate. So I excite this qubit, and now I wait some amount of time and then change the flux bias back to a point where it's strongly coupled. And then what you see is that, you know, here what I'm showing along this diagonal is I'm changing the weight, the delay between excitation and then moving it back to the strongly coupled point. And here you can see nicely that kind of the emission time of our qubit kind of tracks this. So essentially what I can do is I can put the qubit into a storage state where it can hold the photon, it turns out, for about 3 microseconds. And then I can, you know, I arm my source, I can wait, and then when I want to, I can release the photon. And it decays in kind of 50 nanoseconds. So I get my photon out when I want it on demand. And just to say quickly, you know, in fact, I don't have to do just kind of binary, you know, weak coupling, strong coupling. I can tune the coupling continuously. And by doing that, I can actually really, you know, change the shape. So if I just do it quickly, I get this decaying exponential. But if I kind of gradually turn on the coupling, I get something that kind of looks like a Gaussian. Or if I kind of do some funnier things, I get something that at least starts to look like a reverse exponential, or I can at least change the shape. So by tuning this coupling continuously, I can actually change the shape of my single photon, which I think is kind of neat. And I'm going too slow, but let me at least hopefully get through the second part. So far, I've talked about single photons, and I've talked about how we're actually manipulating vacuum fluctuations to do something interesting. So for this next part, I also want to talk about entangled photons, or how we can generate entangled photons from our circuits. So our basic device here is going to be a little bit different. It's still superconducting, but what we have is a microwave resonator. So we just have a CPW transmission line that's, again, terminated. So it's like our last thing, but instead of being semi-infinite, we also cut the center conductor in one place, which makes a coupling capacitor or makes a resonant cavity. So now if I have a wavelength that fits in this physical space, I get a resonance. And again, because my squid is a tunable inductance, by changing the squid, I effectively change the length of this cavity. And so I can tune what that resonance frequency is in situ. Yeah. This again shows what one of these devices looks like. I have my resonant cavity, CPW cavity here. I have, again, another CPW line for pumping, doing fast flux. And this shows my squid at the end with the junctions and the squid loop here with some funny meander. This shows measured, so these cavities for this experiment, we want to access a few modes. So we've designed them so we have up to 3 modes in our measurement bandwidth. And this just shows measured resonance frequency as a function of the control flux. And we see we can tune these a few hundred megahertz on a gigahertz. So now, how do we get to entangled photons from here? So to explain that, I want to just introduce a process, something called parametric down conversion. So this is something that's ubiquitous. So it's used from microwave to optical frequencies. And I'm not going to go into great detail, but basically it's a nonlinear process. So I have some kind of nonlinear media. So in optics, it's a crystal. In microwave, in microwaves, it might be a varactor or a squid. But the idea is I have a high energy pump. I pump this nonlinear media, and through the nonlinear interaction, a single pump photon, or the pump, is split into 2 lower energy photons, often called the signal and idler. Now, interesting point is that if the kind of input of this device, of this thing, is the vacuum, these output photons will be entangled. And the quick explanation to that you can think of as a kind of amplification, in this case, parametric amplification of quantum vacuum fluctuation. I'm putting vacuum noise into this thing and I'm amplifying those. But it's another way of thinking of or getting broken virtual bubbles like I introduced at the beginning. So just putting that in the context of our device, our nonlinear media is just our tunable microwave cavity. We have our resonant cavity at the squid, which provides our nonlinearity. I'm pumping the squid strongly. The resonant modes help because they just increase the down conversion rate at those frequencies. And so if I pump at a sum of two of these frequencies, I get entangled photons at the signal and idler here. So how can we tell if we have entangled photons? So this is real data. So if I pump the thing at 10 gigahertz, I get signals out at 4 and 6 gigahertz that look like noise. I can see I can get some photons out. And like I said earlier, what we're going to do is we're going to look at correlations between them. So for the experts a little bit, as I said, we're looking at something called continuous variable entanglement. And our continuous variables are just the I and Q microwave quadrature voltages. And then the object we're going to measure, which contains all of the information about the state, is just this quadrature covariance matrix. So on the diagonals are the variances or powers of each quadrature, and the off diagonals are just the correlation between these different quadratures or covariances. So this is what we want to measure. So again, we do it in the dilution refrigerator. You can see all of our microwave generators and digitizers next to the fridge. They're somewhat complicated experiments. We have many different filters and attenuators at different temperatures to make everything work out. We also have to do a very challenging microwave calibration. So we have a calibration source at 10 millikelvin and a switch to go in between them. And we have to calibrate the strength of the quantum vacuum, because we're going to compare the power of our signals to the correlations in our signal. And we have to do that at the scale of the quantum vacuum fluctuations. So we have to calibrate quantum vacuum fluctuations at the bottom of our fridge, which is very hard, but we can do it using a calibration source that we got from NIST in Boulder. This is the basic results. So we measure this covariance matrix, and simplifying it, we can say we measure the power or variance P, and then I can subtract from that the covariance. And what I said is we have this bound, which is that P minus C, if P minus C is less than 1, our signal is entangled. And if it's 1 or greater, it's not entangled, it's classical. And we actually did this. We made a classical source, so kind of like I described. I make just 2 copies of a classical signal that are perfectly correlated at high power at room temperature. I feed them and attenuate them into my fridge, where they'll kind of at least they have at least vacuum noise. And then when I calculate this P minus C, I see I get exactly 1. So I make a kind of ideal classical source. But my quantum source, which is my pumping this cavity, as I pump harder, I get out more signal photons. But I also see that these signal photons become entangled. So the correlations become closer and closer to the power. And I won't go into detail, but what's actually going on here is you have the independent vacuum modes at these 2 signals, and they're getting mixed together. So you no longer have independent vacuum between the 2 things. You have a shared vacuum between the 2 signals, and that's why the vacuum no longer spoils the correlation, and this becomes entangled. Okay, so yeah. So for the experts, I'm not really just plotting P minus C. This is the minimum subclectic eigenvalue from the PPT test, but it's basically what this is. And I promised 3 modes in my abstract, but it doesn't really change qualitatively, but the idea is we can scale this. We can put in multiple pumps that entangle multiple modes together. And we've demonstrated, for instance, that we can get tripartite entanglement. And so I was going to talk about a third experiment, which was essentially just actually using this entangled source as a way to do a kind of long-range quantum sensing or improve performance of radar But I'm essentially run out of time, so I'll stop here. And if anybody has questions about quantum enhanced noise radar, which was our proposal, I'd be happy to answer some of those kind of offline or at a different time. Okay, so I'll stop there.
Great, thank you very much, Chris. Yes, thank you very much. This was actually quite a review of fascinating quantum electrodynamics with some practical results. I had scribbled a couple of questions of my own, but let's invite some questions from the audience. So I think there are two ways you can do it. Yes, so we have first one on question and answers, and from Holger, how do you measure single photons from your source? Do you have a single microwave photon detector? Question.
Right, so the way that we do it, so let's see, I can go back. Here, let me move this just so I can scroll through. I'll put this on the screen now. So no, we don't, I mean, single microwave photon detectors are a big topic, but we don't have one right now. So what we're doing here is we're just averaging a lot, right? We just have, in this case, we really just have we have a cryogenic temp amplifier, so commercially available microwave amplifier. Now it's kind of best in class, has a noise temperature of 2 Kelvin, but it's still something like 20 or 30 photons per root hertz. So what we have to do is, we get a single photon out, and it produces a very, very tiny signal. But if everything in our system is very, very stable, we just average, so I think a trace like this is maybe something like 100,000 averages over time. And, then we can see things going out. Now doing that, of course, doesn't tell me that I have a single photon. So we have to do things like these correlation measurements, like measuring this G2. I skipped it for time here. There's something else, a funny thing we can do with this. We can control, I can't really, I don't think I have time to go into this, but we can do other measurements. So we can see that there's funny properties of a single photon that it has no average, a pure single photon will have no average voltage when it has maximum power, and we can demonstrate things like that. But the basic idea is that, we can see the single photon by averaging, but to confirm that it's really a single photon, we have to do these kind of more advanced or higher order statistics measurements. Okay.
Okay. Do we have any more questions here? Well, when the audience, we still have a fair amount of audience hanging around, so thank you. I just learned from our host. This is in fact my thanks to the Angle Media Group, which is helping us to run this webinars. They kindly agreed to let us, basically go with the question period till we wind out, Okay, so the next one, Wilson, max number of qubits you can excite.
So there's a friend of mine, but so I'll answer. So in this system, well, I think we have things where I think our largest quantum systems, not in this experiment, is something like 6 or something like that. But if we want to make single photons, we only need 1 qubit. Now, so there's this other question, so the Bell's inequality. So it's not that it's insufficient. It's just that it's different. So I didn't really have time to say. So this is what I was saying. We're talking about continuous variable entanglement. So we have our continuous variables that are just microwave voltages. But you can also have discrete variables. So something like the spin of a photon or the spin of an electron, right? So that's a discrete variable. And so Bell's inequalities were formulated for discrete variables, things like spin. So if I have a discrete variable entanglement, if I'm looking at entanglement between discrete variables, I can use Bell's inequalities, or there's some generalizations of them. But when I'm looking at continuous variables, I have to do something different. And being fancy, the idea, part of the reasons is things like Bell's inequalities. For discrete variables, I have a finite dimensional system, or my Hilbert, in physicsy words, the phase space or my Hilbert space is finite dimensional. But effectively, when I have continuous variables, my Hilbert space is infinite dimensional, right? I have a continuous, my voltages can take on any value and in a continuous way. So what works for kind of a discrete finite Hilbert space doesn't work for kind of an infinite continuous Hilbert space. And that's why I have to use different techniques for different settings.
Okay. So it looks like, oh no, I thought I got the slot. There's another question. Is there any continuous variable version of Bell's inequality for?
Yeah, I mean, that's exactly, so this really is, where I have it in various places. This really is, I would say this P minus C less than 1, this is the continuous variable version of Bell's inequalities, right? So, and like I said, I gave a kind of hand-waving explanation for this, but this is derived from something called the positive partial transpose test. And so you measure these things called symplectic eigenvalues and blah, blah, blah. But, and you get big fancy formulas in general, or the formulas are more complicated in general, but it does turn out for the simple two-mode case, where if the powers are equal, this is really what that test comes down to. So this really is the equivalent of Bell's inequalities for this continuous variable system.
Okay, thank you. So just the technical comments here. I assume that everybody can view the panel with questions and answers. So if you can basically read ahead to the question, and Chris, you can also view that, right?
Yeah, yeah.
Right. So we do have another question from Luce, and hello, thanks for the talk. How should be a classical thermal state to be considered a quantum state?
Yeah, that's a good question. So, I mean, the short answer is, so, I displayed, there's this equation for the average photon number, this Planck equation. And basically the idea is that, in some units, we can think of the size of vacuum fluctuations being approximately half a photon, right? And so if if the number of thermal photons is much less than half a photon, then the fluctuations in that state will be dominated by the quantum fluctuations and not by the thermal fluctuations. And so it becomes essentially a quantum state. And that's actually, so it gives me an excuse to talk about our calibration source a little bit. So this is exactly what we measure here. So what our calibration source is, let me turn back on I don't have my point, I'll get my pointer back.
It was there.
Because I turned it off. But yeah, so what our calibration source is it's actually just a 50 ohm tunnel junction. And what we do is when we bias the thing, so if we put a current through it, we get shot noise, which just has a known power, 2EI. So for a given, it's 50 ohms, so voltage and current is the same. So I flow a current through the thing. I get a known power out, which you see is very linear. And that allows me to calibrate the gain of my system because I know the power, like the total gain, system gain. And now if I were in the classical regime, if the thermal fluctuations dominated, when I took this thing down the curve, eventually if I go down to 0 voltage, now there's no current, there's no shot noise, but it still has it's still a resistor. A tunnel junction has a resistor, and I would see classical Johnson noise. So down here would give me the temperature of the value of the noise here would give me the temperature of the system. So these things are also used as thermometers. But what happens in our case is because we're in this regime where the temperature is much less than the photon energy, instead of going down to kind of our Johnson noise, we see that we actually saturate at the quantum noise. So this flat level, the reason this thing flattens out like this is I just hit the quantum noise, and now the noise is just flat. So it's just half a photon of noise there. So, I mean, I think this is kind of neat that really in this thing, I see quantum noise or quantum vacuum fluctuations right there.
Okay, well, we have two questions actually from David. Wrote, why is the Bell inequality not sufficient to determine the entanglement?
Or did that one, I think I already answered that one, right?
Yeah, okay. There was 3 or 5, that's right. So this is another one. So
yeah, but then the second one, so again, yes, it's quickly just to say it again, Bell's inequalities work for discrete variables. This is continuous variable, so it's just a different setting. So do the entangled photons really come from the vacuum, or are they just retrieved from the source prior to down conversion? I mean, this gets to be a little bit of an ontological question. I mean, to a certain extent, my answer would be yes. And at least what I would say is that I kind of alluded to this. I mean, this device, this tunable cavity, works as what's called a parametric amplifier. So whatever input state you put in, the output state comes out. You know, or you get an amplified version of that coming out. But if I put in a thermal state, or if I have a state that's not the vacuum, I get amplification, I get a signal out, but that signal will not be entangled. So it's only when the input is in vacuum, so only when I'm amplifying the vacuum fluctuations do I get the entangled signal. And there's other ways of putting that, and I think it comes out from these correlations, because one way of, I mean, now it gets into kind of physicsy answers, but there's an interesting thing that the vacuum state is a pure quantum state, which means it has no entropy. And what's interesting is that if I look at the output of this thing is putting out photons, so you can see it looks like noise. So if I look at either one of these two signals, it just looks like some thermal noise coming out. But because I have the correlations, I mean, ideally, and sometimes we have a little bit of non-ideality, ideally, if I consider those two states, so it looks like thermal noise, so it has a lot of entropy, it has a lot of disorder, but because of this high degree of correlation, the states taken together have zero entropy. So even though it looks like I have these two noisy states with lots of disorder, taken together, they're actually perfectly ordered. So the output state is actually a pure quantum state. So there really is, and in fact, it's actually reversible. So you could go back, if you had another paraamp staring at the first one, you could collapse those photons back into the vacuum state. So you can reverse this interaction, even though if you look at just the single one, it looks like a noisy thing. So it really, yeah, it's a bit of an ontological question, but really you get that it's this connection of, I have these vacuum fluctuations coming in a pure state, and they're coming back out as a pure state. And so it's really this connection, and it's reversible. I could go back to the vacuum if I wanted to. So I think there really is a real way in saying that it's coming from the vacuum, or a vacuum at least is important. Now, there is another way of saying that, it's like there's energy, there's real energy going out, and that real energy, of course, is coming from the pump. So it's not that the pump isn't involved, and the question of whether it's really is this really virtual photons? I think it is, but I think in any case there are very deep connections between this kind of the incoming vacuum fluctuations and the signal going out.
All right, so looks like we don't have right now any questions. We probably cannot really carry on for too long, but let me just try to smuggle my question here. So this is a pretty amazing situation where you can tune out those virtual photons and their noise, and you can extend the lifetime of your of your quantum state, sort of arbitrary. This, I don't suppose this is a technique which could be applied for higher energy photon easily, right? I mean, are there attempts to push it into infrared or into visible?
I mean, I think there, so so I think as physics experiments, yes. So people have done kind of real single atoms in front of mirrors just to see the suppression of this vacuum fluctuations. But in a more prosaic sense, well, in a more usual sense, I mean, this is exactly what putting, say, like an atom into a cavity does. So if you make a cold cavity, when people do kind of quantum optics experiments or cavity QED experiments, because again, so it's an interesting point that, and I kind of try to hammer this home for my students, all of the shape of the modes and the frequency response, so if I make an arbitrarily complicated circuit with L's and C's, or I make a cavity or something like that, the frequency response of that thing is fully determined by the classical physics. Like I can just write down the impedance function of my circuit. And so, filtering works for vacuum fluctuations. So a cavity just filters out vacuum fluctuations, right? So it, like a, physical optical cavity, it just says that, vacuum fluctuations that aren't resonant get suppressed and vacuum fluctuations that are resonant get enhanced, right? And here I'm just doing it without a cavity, but it's, I'm using my classical intuition of kind of interference and standing waves, but it's the same basic idea. I can use my classical intuition about how I can suppress things with interference or resonances, and then that carries over to the vacuum.
So, but in the end, of course, that is kind of, other than beautiful physics and the way of influencing it with all the fancy equipment and neural circuits, of course, in your brain, it is going to down the road serve as those conduits to communicate between the quantum nodes, perhaps, right? And with working with microwaves in this particular technique, does it set some upper limit, which is a bit slow for communication?
Well, I guess there's lots of things. So I think there may be niches for microwaves for kind of long distance communication. But I think, generally for long distance communication, you think about using optical photons, but also thinking about, on chip. So if I build a quantum processor out of little processors and I can use these techniques to say distribute entanglement, on chip or maybe between fridges. But in any case, but there's lots of people working on, there's a lot of ideas of thinking about, maybe having hybrids where, say, I have quantum computers built out of superconducting systems, sitting, at various nodes. And then, what I need to do is I need to convert microwave photons into optical photons when I want to do long distance communication. And there's actually lots and lots of people working on trying to do that. So how can I convert microwave photons to optical photons, and doing things that, in various systems ranging from atomic gases to nanomechanics and things like that, or optomechanics. So it's an open problem that people are working on. How do I convert these quantum microwaves into quantum optical photons and back, so I can do this communication? And again, this isn't so crazy if you think about how a lot of our classical communication works, right? Our computers nowadays are really gigahertz, they're microwave systems, right? You have gigahertz signals, which are microwave signals moving around, electrical signals. And when I want to, when I, plug in my Ethernet, there's some card that maybe, well, if I have an optical connection somewhere, or maybe out on the telephone pole, that gigahertz electrical signal is being converted into a gigahertz an optical signal with gigahertz modulation, right? So there's some point where I have an microwave optical converter, in my system, right? So, now we just want to do that in the quantum regime.
Okay, well, thank you very much. So we don't have any more questions, and really we also really have to wrap it up. The closing comment here, we intend to put the presentation and future presentations on Waterloo University YouTube channel somewhere. There typically is a place for some discussion, so we'll see how this works out. And for now, I just would like to thank you, Chris, for a very interesting talk, and for the great discussion which follows the audience, and for those who stayed on. Thank you very much, and I guess that's it for today. Okay, so have you? I think I will just wish you a safe weekend ahead. Don't go into the crowded places too much. Okay, and we will close the meeting at this point. So
Okay.
thank you.
Thank you everyone for attending.